you very much for the introduction. Good morning. My name is W.Lee from Busan National University, South Korea. The topic of today's talk of mine is about the size fact. The material was 316L stainless steel, and yeah, I will show the result. And this talk is about the laser powder bed fusion process, which is the big topic of this whole conference. And when I first started the printing job, most of the mechanical engineers, they wanted to produce the components of something like this, like the replication of the casted or the machined material, so with the same size and same geometry. But now, at least in Korea, many of my colleagues, they go to the direction of using such lattice structures or the topology optimized structures. So in these cases, size effect is very, very important because we have some small features inside as the internal structure. And that's why we started this work. And our main question was, indeed, do we have any strong size effect in the powder bed fused 316 stainless steel alloy? That was the main question. And this is actually the typical microstructure of mine from our LPBF facility. And probably the microstructure is pretty much the same for every kinds of laser powder bed fusion process of this material. We have laser bead and some unique microstructure and grain structure, which is normally characterized as the fine grains with some texture. But we always consider this material as the homogeneous one. But if there is, we consider those internal structures or the small feature size, then there is one additional thing that we have to look at, which is the laser contour scanning. This has been used popularly, most popularly for many of the commercial LPBF systems, at least what has been integrated with the Magic software. That is that if we fill in one layer with zigzag pattern, then we have some kind of stripe pattern on the surface because of the surface tension. And this is actually bad on the point of view of the surface quality. So to get rid of the stripe pattern, we usually do an additional laser scan on the outer surface so that we don't have any more of the stripe pattern. But if our component size is big enough, then this area is, maybe the effect is negligible. But if we have some kind of lattice structure or the internal structure that has the size small, then the area that is influenced by the laser contour scanning would influence the overall performance. And there are several studies already that we have completely different microstructure near the outer surface of the LPBF for whatever reason, maybe from the contour scanning and maybe from the unmolten powder and so on. And there are also some studies that we have slightly different local mechanical properties as well. For instance, local micro hardness can be varied from the core to the outer surface. Usually it's higher. And from those questions, our motivation was to study if there is the effect of the contour scanning on the microstructure and mechanical properties of the 316L stainless steel. And actually, indeed, we found that there is strong size effect. And then our motivation was to investigate the effect of annealing heated quantum because we want to investigate the origin, and also to develop a simulation model to quantitatively estimating the size effect so that we can use it for the designing the component. So So for this, we have developed one special experiment. Here is our specially designed tensile specimen shape. Here we have 4 different types of the specimen geometries. It's basically tensile specimen, and sample series 1 has the simple geometries such like the normal tensile specimen, and sample series 2, 4, 8 has divided beams of the tensile gauge length. So we are basically increasing the surface area while keeping the overall cross-sectional area the same. So if there is some kind of influence on the microstructure of the contour scanning, then we are basically increasing the area that are influenced by the laser contour scanning. And we produce samples in 3 different directions on horizontal plane, vertical plane, and 60-degree plane to the building direction. And we produce another small sample for the microstructure investigation. And here it is, EBS microstructure clearly shows that we have slightly different grade structure here near the contour in comparison to the core, and on the vertical direction, and also in the case that we have upskin or downskin. Downskin, we have really fine microstructure, and in the vertical sample, if we measure the local hardness by the nano indentation, we found that the nano hardness at here near the where the laser contour scanning is put is pronouncedly higher than in the core. And actually, this work has been published quite recently, and we suspect that this was due to the different heat flow that influences the solidification rate, because when we first scan the laser, then one side is always with the porous powder layer, which has less thermal conductivity, and if we scan laser twice, which is the case of the laser contour scanning, then our melt pool is always surrounded by the already consolidated solid, so probably the cooling rate or the solidification rate is slightly higher. That was our hypothesis, but the reviewer raised one question that this or this might be due to the molten powder. Yeah, yes, it is, that's possible, but we still believe that there is the difference in the solidification rate, because we checked solidification cell size and we found that near the contour scanning region we have much finer solidification cell in comparison to the core part. So looking at the mechanical properties of those specially designed samples, the size effect was really pronounced in the horizontal direction. As we can see here, the black line is the sample number 1, which is normal shape. And when we increase the area of the laser contour scanning, then we are basically increasing the yield strength and decreasing the elongation. And this effect was the most pronounced in this direction, but there are such effects with the same trend in the different directions as well. This is to summarize the result, where we can see the clear trend that in every direction we are increasing the yield strength and the tensile strength, and decreasing the maximum elongation by increasing the or decreasing the feature size. And so to figure out what is the real origin of this effect, we did the heat treatment. We used 2 different heat treatment conditions. Here, I didn't bring any optical microwave, but this condition, 750 degrees for 30 minutes, this we call internally as the stress relieving heat treatment, where we don't change any microstructure, but we don't have any distortion anymore. And here in this case, we call it the homogenization heat treatment, where we diffuse the solidification cell. So we selected two different conditions and checked the mechanical properties again. And in the case of the stress relieving heat treatment, we are reducing this effect, but we don't get rid of the size effect. And in the case of the homogenization heat treatment, we can really get rid of this size effect. So that's why we suspect that those are really strongly influenced by the solidification cell size on the contour scanned area. And finally, we have developed a very simple model based on the microstructural understanding of this. We considered the contour scanned area as the slightly different material for the later on for the use of the design, and along with different directions. So here in the cross section, we can see that the red is the surface area where the laser is scanned twice by the contour, and gray is the core. And by fitting with the experimental results, we could really reproduce the size effect with this very simple finite element model, so that can be used for the mechanical engineers. And here's actually the reason why we have the size effect. So if we look at the finite element result, then the core contour region is slightly stronger in the yield strength. So while we apply the tensile load, then here is where stress is concentrated, but here in this case, the effect is not really strong, but while we are increasing the surface area, then the portion of the strong material becomes larger and larger, and then influences the overall properties. So to summarize, our main question was that is there any strong size effect? And the answer is yes, it is, and we believe that for this particular material system, this is from the contour scanning that influenced the microstructure and mechanical properties. And this effect seems particularly important in structures that include thin beams or struts, such as lattice structures. Thank you very much for the listening, and this is the end of my presentation.